Fantastic, I can see what I'm supposed to be saying. Okay, let's just get on with it then, I guess. Unless there are any objections. You may be able to tell, I've not really done this before. Okay, so, title of the speech. Speech presentation, let's go with presentation. Yeah, ElectrEm UEFs Cluck and more me, because I do not do these things often. Yeah, so I wrote ElectrEm way back when, in the 1990s. These dates are approximate because my memory is approximate. I remember having ElectrEm mostly working before I started university, so that's definitely 1999. Don't really remember when I switched over to ElectrEm Future, but yeah, around then, probably. And clock signal was recent on that scale. So yes, the very first version. And again, remembering that I wrote this before I had even started university. Single-threaded, fair enough. I think that, as it says in bullet point number 4, the original platform was MS-DOS. So unless I wanted to be very clever and use hardware that I didn't have, single thread, there it is. One big switch statement on the next opcode. This is very classic emulator layout stuff. You know, switch on memory, square brackets, program counter, jump on down, do a whole operation as though it were atomic, i.e. all memory accesses, reads and writes sort of occur one instant, just like that in this model of emulation. Do that for around 128 cycles on the 2 megahertz clock, and then update the video, the audio, and a whole bunch of anything else that needs to be updated right then. For example, when I first added the WD1770, the +3 and all that, bytes from that would only show up exactly at the end of scan lines, which, I mean, philosophically, it could happen in real life, but like 1 in a trillion shot. So if you were software, you would be able to tell, but it would nevertheless be a scenario you're supposed to cope with. So I don't know where you want to fall on that. Is that good? Is that bad? I don't know. Yes, so after MS-DOS, I went to GGI, SVGA, lib, STL, everything else that was cool around the year 2000. And yes, as per the final bullet point, the biggest obstacle getting it finished is Chucky Egg, because this is an aspect of emulator development I feel few people touch on, which is that as soon as your emulator is good enough to play things that are fun, you will then spend your days playing things that are fun rather than writing your emulator. This is my pet theory as to why there are so many Nintendo emulators that run only Super Mario. People go, yeah, that's good. That's the essence of the platform. That's everything I wanted to do. Done. So, starting on ElectrEm motivated me to invent the file format that some people, I'm sure, if I had the gallery up now, would now be rolling their eyes at the mention of UEFs. Haven't even bothered to spell out the acronym. It was Unified Emulator Format. So, coming to the Acorn world of emulation, of course, I have a real Electron back in the day. There were int files, and there were SSDs and DSDs. There was nothing widespread that captures the essence of a tape, and unlike the BBC, that's a potentially controversial statement, but now I'm going to have to roll with it. I would argue the Electron was primarily, for most people, sort of a tape-based micro. It was like the Spectrum competitor was there with the Auric and the Dragon, and going down to the newsagents and spending £1.99 on some Mastertronic game that turned out to be terrible. So, in order for an emulation to feel like the real thing, it would be necessary for it to emulate tapes, therefore a tape file format was needed. But being a young person, not necessarily yet well experienced in the idea of appropriate scope, naturally, I said, well, if I'm inventing a file format, I'll just put everything into it, because that will be great. So yes, as per the second bullet point, there's on-tape data, which is intended to be at a sufficient precision that it, in one sense, accurately portrays what was on the tape. Of course, you can get into fairly semantic arguments about at what point you become accurate in representing something shy of modeling I don't know, magnetic molecules or something. I am not good at science, forgive me. In addition to on-tape data, that UEFs can, in principle, emphasis on in principle, hold disk images, state snapshots, scans of inlays, text blurb, which platforms this file is for, etc. So the idea was that everything that you would obtain if you went to your shop and bought a piece of Electron or BBC software would be recorded within the UEF. And yeah, it's great to have a grand design. I admire my youthful vigor, but when I then came to implement them, as per the later bullet points on this page, all I really provided first time around was a tool called Make UEF, which allowed you to attempt to read your Electron tape in ROM format only, in the sense of, like, Way of the Exploding Fist is the only one I can think of that has a custom loader on the Electron, but, oh, maybe Spy versus Spy too. Anyway, yeah, so data recorded on the tape as though it had been recorded by the ROM was the only thing the original Make UEF supported, and it would write it out in a regularized format, so it would enforce its own sense of what the timing should have been. And there was no way to say which platform this tape is for, or here's an inlay scan, or here's some text. And as a result, those features have, to my knowledge, never once been used. And they are not widely implemented, and we should all just accept that in practice, they do not exist. And I also have to give thanks here. That was an awkward segue, but I'm going to give thanks anyway. Fraser Ross and Greg Cook, who have also helped out with improving the UEF file format over the years. You will notice if you ever try to implement it that one of the late bolt-ons, some of the late bolt-ons are things like floating point gaps, because apparently it never occurred to me that the space between data might not be exactly a whole number of bits. Stuff like phase and other aspects of an analog tape signal that probably I did not understand in my youth. It would have been nicer to have been able to incorporate those things on day one, but I did not. So, onwards. Electron Future was the cycle perfect rewrite slash, it wasn't really a rewrite, it was an adaptation. And it shook things up quite a bit. So as per the first bullet point, instead of being single-threaded, it might as well be single-threaded, but in fact cooperatively threaded in order to give me coroutines. So there is one processor thread which still has a switch on, which opcode, and then jump to the thing that implements that opcode. But now it is potentially blocking, so it does all its reads and its writes in the correct order, and it announces them one at a time, and it can block at any time, and it is its own thread. So when it blocks, it gets to keep its heap, stack rather, would be the more interesting thing, and then resume later. So there's a quick semaphore, so there's technically multiple threads, but they're cooperatively scheduled, so it might as well be one thread. I just wanted a coroutine. In order to make it cycle perfect, just imagine the inverted commas every time I say that, because I don't even really like the term. It's kind of reductive. It collects video memory as it goes. So video memory is also collected at the right time without having to jump too much between code. That's more of a, implementation nicety. And then outgoing facts like, audio events, palette events, they are just time-stamped. And then when it gets to end of frame and I'm like, I need to construct the frame, what it looks at, it has a big buffer of all the video memory that was collected, and it was collected at the right time, and it knows when things like palette changes occurred within that set of collected data, so it can redraw the whole frame correctly as if it had been doing it in lockstep, even though it wasn't. Of course, the only exception there is mode changes. A mode change affects how the CPU will collect memory from that moment onwards, since obviously you can't apply those post hoc. So yes, it would have been cycle perfect, and indeed, prior to about 2016, I had always believed it was, but there's an off by one error in the 1 megahertz to 2 megahertz transition costs. The Electron there acts very similarly, I now know, to the 1 megahertz bus on the BBC Micro. So if the processor is running along having a lot of fun at 2 megahertz and it needs to access something on the 1 megahertz bus, which in the Electron is always the RAM, and even then only if the RAM is currently available. Of course, it has to stretch the cycle out because the 6502 is purely synchronous in its memory operations. So that stretch should cost either, the access should end up costing either 2 cycles or 3 cycles, but in ElectrEm it costs either 1 cycle or 2 cycles because I had a broken mental model about how that interleaving works. So that's a shame. Also, all frames are the same length. The Electron, I think Paul Body has subsequently discovered, produces interlaced frames, and the real-time clock interrupt, which occurs in the middle of the frame, therefore occurs alternately either at the beginning or the end of a scan line. So the frames, it is measurable. A piece of software can tell, am I in an odd field or an even field? And I did not emulate that in ElectRem Future because I did not know that, which is great. I'm acquitting myself well here with fantastic excuses for things. So, oh yes, Ewan Roberts provided an OS 10 port at the time. I did not have a Mac yet, and that kind of saved the day for me. Global financial crisis, I was in publishing, the iPhone was big. Here I am, whatever, 12 years later, still a software developer because I was able to say, oh, I know some Cocoa, it'll be easy. More youthful. Here we go. Clearly I was a youth for a lot longer than I'm willing to admit. Let's move on. Clock signal is the new one, or as per the subtitle there, it is the new 2. So yes, there was an original emulator called Clock Signal, which only did the Z80, boo hiss. Its big thing, and this is from where the emulator derives its name, was that the only piece of shared state is the bus, like a real computer. And that's just a 64-bit int with all the relevant signals recorded, obviously not like +5 volts and ground or anything, but all of the data carrying lines are represented as a single bit in the int, and the int goes around whenever people want to see it. There's actually a complicated system whereby components register themselves to the bus. They say, I'm interested in only these lines, and I'm interested only if anytime they transition or anytime they have this value. It's, I played with that a lot to try to optimize the thing, but as for the second bullet point, I never managed successfully or satisfyingly to optimize the thing. So I was only emulating the ZX80 and the ZX81, which run at 3.25 megahertz, but the whole thing that clocks the emulator is the clock signal, hence the name, which of course rises and falls twice per cycle. So that's like, whatever, 6.5 million circulations of a new bus state per second. And if you've got a bunch of components listening for that, and you also have to do the logic to decide whom to notify, you end up spending a huge amount of time just deciding where you should be propagating information. And the emulation itself, certainly as the user experience, is not all that enjoyable. I think probably at the time I was using a MacBook Pro. At the time it would have been, I don't know, like an i5, something. I was using 70–80% of a core just to emulate a ZX80/81, which was making the fans come up and everything was hot, and it wasn't fun. So put that aside, and a few years later decided to write the smarter follow-up, which is the new clock signal, the current clock signal. This time started in 6502 because of my emotional attachment to it. It nowadays also has Z80 and 68,000 micros in it, which I guess I can elaborate on later. But instead of the single unit of communication being any transition on a bus line, it is any atomic action on the bus. So if you look in data sheets for things like the 6502 and Z80, as I'm sure probably 90% of people here have, there's usually a section of timing diagrams, and they will say something like, you know, a read cycle looks like this. The RW pin will be valid from this many microseconds after this clock transition, and then I will sample the bus at this location. So a lot of the time with processors, not so much the 6502 as per the final bullet point, but for the others, more so, all you really need to say is, this is going to be a read cycle, and I'm about to do the first 1.5 cycles of it. That's a Z80 example. It samples the wait line as an awkward time, but there it is. Which means that if you are talking on the lowest level at which, or rather the other way around, the highest level at which you have not omitted any information, then you are having to say a lot fewer things. You are saving all the costs of propagating, so you're still cycle accurate to the extent that means anything, but it costs less. Fantastic. Life is great. As per the bullet point, though, since the 6502 is a processor that performs a read or write every cycle, pretending there were no ready line, but that aside, a read or write every single cycle, it looks almost identical in that case to just classic cycle-by-cycle implementation, but it doesn't look like that for the other two processors. And nowadays, almost everything in the emulator is counted in half cycles rather than full cycles for that reason. Other aims going into this new version of the emulation, designing for users. And this is why I indicated that I was an iOS developer for a while, because I think I may have been conditioned. This is, I don't know, some sort of syndrome. Clearly, I like things that just work. I do not like the sort of emulator you download, and I've done this recently with an Atari ST emulator that was particularly dreadful. You've got to launch the application, you've got to configure the sort of machine you want. Often they have some UI the user knocked up, which barely functions. This particular Atari ST emulator, the buttons don't click. You have to furiously tap, 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 tap in the hope that eventually you will register a click. The objective of this emulator is that you or I can go to our friend who has never used an Acorn and say, you should stop playing the Spectrum Chucky Egg because the physics are terrible. You should play the BBC Chucky Egg because it's fantastic and your life will be better. And they can just grab the SSD or the UEF, double click it, emulator launches, game loads, they're playing the game. They don't have to know how you're supposed to configure the machine underneath, how you're supposed to load things on this platform, or any of that nonsense. They can just double click the file, game launches. Fantastic. And of course, that's not just for the Acorn, that's people like us might benefit from that if somebody else tells us to play a Commodore game, and indeed, if we are so willing, having had one recommended to us. And how it achieves that, then, this is, I watched the two previous presentations on JSBeeb and BeebJit, and this is my attempt to find something interesting and unique to say about my emulator, even though it is not doing anything as interesting as being written in JavaScript or recompiling code just in time. So, ahead of time static analysis. Some of that is pretty obvious. You just look at, for example, a floppy image. Is it MFM, or is it FM, or is it Apple GCR or Commodore GCR? Look at that, fine, you've already restricted your options. If it can be read as, say, MFM, let's do the Acorn example, then does it look like it has a DFS or ADFS filing system upon it? If it does, well then it's probably an Acorn disk with the appropriate ROM selected. That's kind of where life ends for Electron emulation, because there aren't that many variations in that particular piece of hardware. But supposing we were talking about something more like, say, a VIC-20, where there are a multiple variety, let's pretend that was a meaningful sentence. There are many different RAM expansions to take the VIC-20 to many different sizes, and the smart thing about the VIC-20 is it moves where the display file is based on how much memory you have, and then software for a certain amount of memory just assumes it knows where it is. So you have to kind of exactly guess which RAM expansion goes with each piece of software. And this emulator will attempt to do that in extremis when necessary by actually looking for what appears to be the first file that is of interest with this particular title, inspecting if it's basic, disassembling it, if it's machine code, trying to see what hardware it hits, what addresses it thinks it lives at, and so on, in an attempt to automatically configure the appropriate hardware and then issue the correct loading command. And it tries to do all of that for you, again, so you can just think, I want to use a piece of software from the 80s, fine, I will use that piece of software, and oh, it's emulated, whatever. I don't want to think about the emulator should be invisible. This is all for invisibility and, I guess, platform tourism. Unfortunately, static analysis is not always, it may always be possible, but I have not managed to make it always possible. It is, in many cases, very difficult. So in that case, the emulator will go into dynamic analysis. So there's the simple sort where it will simply, where possible, detect which hardware a machine should have at runtime based on which hardware the software is trying to access. Possible sometimes, not always possible. And the less simple sort, when it still has no idea, it will simply say, well, there's only 3 or 4 possible options here. Let's just try all of them until one of those machines falls over. And it will be running, in this example, 4 machines simultaneously, and it will have a bunch of switches and triggers so that it can estimate how likely is it that each of these machines is the correct one, and it will show only the one that is the most likely to the user. And when the others drop below a certain threshold of probability, it will stop running them entirely. And at no point will it tell the user it's doing this, it will just happen. Usually, in practice, empirically speaking, it seems to manage to resolve these situations relatively quickly, which is nice because optimization is something that I could possibly spend more time on. That's the polite way of phrasing it. But, so some concrete examples, I guess, would be helpful on this slide. If you give me in this scenario, I'm an emulator, which will be a new experience, a 32 kilobyte file called something something something.rom, and it appears to have a valid CLKvision header in it. It nevertheless may be, amongst the machines that I emulate, a CLKvision or an Atari 2600 ROM. There is no way to be 100% certain on the nail, so I will just simultaneously run an Atari 2600 and a CLKvision, and at some point one of them will crash badly. In that scenario, it will be either, well, actually, so in practice, 32 kilobyte ROMs tend to go with the CLKvision because it's a later platform, and the Atari 2600 tends to crash very quickly because this is a very manual system to run with its, the user has to manually run the display on a 2600. Nothing much there is automated. So ordinarily, that will resolve itself very quickly. The other big scenario that the emulator tends to have to deal with in practice is MSX cartridge ROMs larger than a certain size and guessing what the paging hardware in there is. And sometimes those don't resolve for a very long time if they happen to have put, say, the title screen in the first bank, which is commonly the first one paged by all the mapping schemes, and it just sits there for a very long time until the user actually starts playing. It may not be able to resolve that ambiguity. But also, the problem there is that each of them appears to be equally valid, so the eventual switch down to whichever was correct will be entirely invisible to the user. So that's all fine, other than, again, their fans possibly coming on. That's great. So, also, having spent so much time as an iOS developer, which I'm not now, by the way. I do server stuff, C++, low latency trading. I'm basically the Matt Godbolt career tribute act. Google and then trading, that's the main two. But yes, in the mobile world, of course, you're trying to optimize for power efficiency and a much smaller processing footprint per core in total, at least in the days when I was doing it. So thread everything, try to thread everything. So here's the threading model for clock signal, which is more in depth than I had implemented before and therefore potentially interesting. Who knows? We'll find out at the end. Yes, there is one main thread for each machine. This emulator runs multiple machines at once. If you want, you're the user, all the windows open, put them in tabs, whatever you want. So one thread per machine is running the stuff that I'm going to have to add a caveat to in a moment, but let's just call it the stuff that is necessarily synchronous. That is, all the parts of the machine that run on the same clock and may talk to each other unpredictably. So that looks like the main thread of most emulators, subject to the caveat that I'll get to in a minute. Audio events are posted off to a separate thread called the audio thread, because, creative literature, always been a skill of mine. They occur or are posted and are generated at the native clock rate of the machine, or usually close thereto. So on an Electron, there is at some point in memory, or there may be, I may have changed this since, but a full-on 2 megahertz sampled, I guess in this case it's a 1-bit wave, and it gets a 1-bit wave. I don't think the off is different from, speaker low. And then a full-on resampling of that down to whatever the output rate of your machine will occur. There's more on this on the next slide, so I'm going to skip over specifics on that. There is another thread for what is currently OpenGL stuffing. Of course, thanks to Apple's WWDC, it will not be exclusively OpenGL in the future, but for the time being it is. So, I mean, the reason people are moving away from OpenGL is that it doesn't thread all that well, and the amount of effort it puts on the CPU just to provide that particular API over modern GPUs is, you know, quite far from zero. So there was a separate thread that just does all of the talking to OpenGL. Keep that in its own little box. And of course, the on-GPU processing is parallel with that again. So I mean, maybe you'd want to argue that was heterogeneous threading, but I probably wouldn't because that's stretching things a little. And then there is there are multiple thread pools for ephemeral works, such as the example there is transcribing flux back to SSD. I guess I will hit the final bullet point, then possibly segue back into the interesting side point there, I guess. Yes, some machines go a little further, allowing just-in-time components to float off into a separate thread when they're far enough behind. So this is a technique, possibly the thread bit isn't, but just-in-time processing is a technique most emulator authors eventually hit upon / prefer, in which, say, let's just say the video chip again. No, because that's a bad example, so let's not say that. The audio chip in a generic computer or just single channel in an Electron. Instead of running it in lockstep, so instead of saying one CPU cycle, one audio cycle, one CPU cycle, you just keep a count of how long it's been since you ran the audio chip, and the next time you have to interact with it, you say, oh, just in time, run the audio chip to catch up to where I am now, and it will be as if I was running it all along because nothing can have modified its state in the meantime, and that will be exactly as accurate as if I had been running them in lockstep. That will be much nicer on my processor cache, instruction cache especially, data cache also, I guess, depending on how much state there is associated with these things. It's just an all-around smarter way of implementing things. And in this case, I have added, for some machines, it's opt-in, feature whereby if you are running like that, and you notice that in this example still your audio chip is, say, whatever, 10,000 cycles behind, and you are aware that on your system it actually costs only 100 microseconds to issue some processing out to a thread pool, and you're aware that it will take more than 100 microseconds to catch up that number of cycles, then you can kick that processing off to another thread. This is when the things that are nominally synchronous stop necessarily being so. And hopefully, if you're lucky, the processor won't attempt to talk to the audio chip again until that processing is finished. If it does, you're going to have to spin lock and wait for it to finish as though it had been synchronous the whole time. But a lot of the time, that means you can parallelize things, I don't want to say for free, but for cheaper than if you'd run them in a more traditional fashion. So a machine where that works, or a family of machines where that works particularly well, are those based on the TMS 9918 and its derivatives, such as the Sega Master Systems. That is a video processor that has its own pool of video RAM, and it is accessible to the CPU only by saying, by writing an address you want to access, and then writing a value you want to write, or alternatively waiting enough time and then reading. So in terms of video memory collection, that doesn't really need to happen synchronously. You can just do that on demand even, which means that it is more disjoint than a classic shared memory pool, such as the Electrons. And that is actually emulates a bunch of systems like the CLK, the Master System, the MSX, the SG-1000. These are all very similar in this regard. And for those, if I use this technique to break the video processing, it's in the actual, turning bytes into pixels stuff into another thread, then actually the costs are very similar, which is, therefore makes this one of the most successful multi-threading approaches for emulators such as this. Unfortunately, the net total ends up being very similar. And with modern emulators, the net total processing footprint, even when you're allowing for the fact that scheduling is going to accrue a whole bunch of time that you don't really want to pay for. I'm verging slightly off topic there. you're looking at like a 10%, 20% processing floor, I would imagine, for any processor, any emulation that is trying to reduce latency. And even when you float these things off into another thread, you're still looking at a 10%, 20% floor. So I don't tend to do that at the minute. I'm going to hold that in my pocket until I try some more complicated machines. I've got the Neo Geo in mind one day, but I've got a lot of things in mind to do one day, and we'll see. So here we go, output, where most of the cost accrues. Whoop. Yes, so as I said, audio is generated at the machine's native clock rate, by which I mean the emulated machine's native clock rate, and then filtered down to your machine's native output rate. And on the Mac, I get to use the sim unit for that because there is a thing called the accelerate framework that just means I call, one function instead of doing a for loop. But in the cross-platform version of the code, I've just got it written in plain C++ because I didn't even want to use GCC-specific extensions because I want to do a Windows port one day. Again, a thing that I want to do one day. So yeah, there's generic C++ code, there's a Mac extension, fine. If there are any mathematicians on the line, I'm specifically using Kaiser Bezel. So a fur filter looks like a weighted sum of a finite number of items when you do it in discrete data terms. So basically you're looking at, say, for argument's sake, pick one. It's usually an odd number because the weighting is symmetrical. There is a center point. So you got to produce each output sample. You look at, say, 21 input samples, and you produce a weighted sum of them. And the weights have been calculated, well, by a variety of ways. But if you want to just imagine it in like simple terms, imagine a normal Z transform, that is a transform from the time domain into the frequency domain, like MP3s do. For example, you can kind of get away with just plotting the frequencies you're interested in the frequency domain, translating that back to the time domain, and using those as the weights, sort of. Not really. That was a bad explanation. Hopefully there aren't any mathematicians here. I take that back. Okay, so video is actually one of the other interesting things that the emulator does, for the reasons that I will now endeavor to explain. All of my machines, including the Electron and the ones that are worse than the Electron because they're not Acorns, they all produce video as a 1D signal, like a real machine does. A similar machine doesn't have a separate sync pin, of course, but assuming it doesn't, yes. Well, I suppose it is still a 1D signal, it's just got more components to its one-dimensional vector. I don't know. I'm going to stop thinking about that extemporaneously. So there's an emulated CRT. It will try to separate the sinks, and it will try to say, oh, this one is a horizontal sink because it was short, and this one is a vertical sink because it was long. With regard to that, I've implemented, with regard to the whole system, what I tried to do was find a bunch of textbooks from the 1980s and at worst the early 1990s on how televisions work, which tended to be repair manuals, so mostly went over my head. But as I understand it, a TV of that era will often do this as like a horizontal sink. It will figure out by a sort of semi-differentiation type approach, as in any time you jump to the sink level, it will go, oh, that's probably an attempt to indicate a horizontal sink. And it will attempt to do a vertical sink more like an integral thing. So you'll be charging up a capacitor for the amount of time that you are indicating the sink level. And at some point, that capacitor will be, I'm going to now reveal my lack of a formal basis in analog electronics, but at some point that capacitor will be, in my very simplified understanding, full, and then it will somehow discharge or something, and then the CRT will say, oh, well, that was the user attempting to signal a vertical sink. But in both cases, of course, it may be dealing with a noisy signal, so it doesn't actually just take those commands at their word. It instead attempts to phase lock to them. In my case, I'm using a simple flywheel type phase locks loop, possibly with some prima facie windowing, but I think not. So at any given time, the emulated CRT knows that I should see the next horizontal sync, at time X, and then if it sees what it thinks is an attempt at a horizontal sync at time x plus n, then it will say, oh, it was later or earlier than I thought, or it was later than I thought, then obviously, you know, I should slow down a bit here and scan less quickly left to right. And if it was sooner than I thought, then, oh, maybe I should be scanning left to right a little bit faster. And that will adjust its prediction of when the next sync will be. But when it will actually do a vertical retrace is whenever it predicts the next one should be. So you can influence and eventually get into phase when these syncs are happening by providing a proper steady signal. If you provide a noisy one, it's going to jump and it's going to roll, and these things matter a lot on machines other than the Electron, where you have programmatic control over the timing of synchronization, which in my emulator includes the ZX80 and 81, the Atari 2600, and of course the Amstrad CBC with its 6845. So the same logic would apply if I were to add the BBC Micro. I can't imagine anybody would get, well, no, actually. So a nice effect of the way that a display bounces if you get the sync wrong ephemerally. The nice way that looks, that little bounce means there are a bunch of games out there that just use it for a nice like explosion effect or something. Just, you know, you just got hit by a big mortar, throw the frame out of synchronization for a second, let it bounce around a bit. It'll look like you're in a tank being hit by mortar. It's fantastic. No processing time spent. So that sort of effect should be accurately portrayed. And, well, there are some interesting things to say about composite video as well, I guess, but I will tack that on as a mental fifth bullet point. Yes, so the other thing this does is that drawing to your host machine is pull instead of push. Specifically, the emulator is, at least nominally, there is some, you know, wiggle room on claiming this with regards to the way these things are scheduled, but it is normally always maintaining an emulator CRT, and at any time you can ask, what does the CRT look like now? There's no inherent need to ask anything in terms of what was the last frame. I think V2 works similarly to this, so this is not the only emulator that does this in Acorn world, but that means that if your host machine is running at, say, 60 Hertz or 120 Hertz or 144 Hertz, then it can display for you 60 different pictures a second, or 120 different pictures a second, or 144 different pictures per second, even though the machine being emulated is running at only 50 frames a second, or fields, because as I say, we have learned the machine is interlaced, which has a couple of benefits. Number one, it helps to reduce motion aliasing on the most common bog standard 60 Hertz displays, such as every display built into a Macintosh. And I guess many other computers, but my experience is limited nowadays. So motion aliasing is gone, and if you are a gamer and you care a lot about, you know, latency and things, and you have a 144 Hertz monitor because you are a person who spends money because you care, then you will get a much lower latency output. So your money will be well spent. You can congratulate yourself on a successful life. Yes, so there is only one slight caveat to that. The two things are not completely decoupled, in that if the emulator spots that the machine being run is going at a similar rate to the host, and that includes integer divisors of it, because I'm sure I can't be the only one who decided they wanted a 4K monitor from their very old computer and therefore has to run it at 30 Hertz, but that is why that is implemented. If they're running at a similar rate, then it does yet another phase locked loop, because that is the catchphrase for this slide, to try to force the emulated machines sync into phase with the host machine so that you will not see tearing. And that may involve slightly adjusting the rate the machine is running at. And I think I have more on this on here. I do. Fantastic. So, I mean, the adjustment will never be large. It's more like, you know, again, let's pretend I'd implemented the BBC Micro, even though I'm not quite there yet. You know, you've configured the CRTC, so you're actually running at, you know, 50.83 Hertz or 49.97 Hertz, and your monitor is 50 Hertz or 100 Hertz. You know, just, you know, slightly adjust the rate at which your machine is running in order to match your output display. And I'm going to offer a bit of defense in advance there, although I am very obsessed with accuracy because I'm an emulator author, and that's how we all, you know, say, oh, I'm the best, I'm more accurate than you. There are kind of two inaccuracies that can come out of not matching them up when they're close. Inaccuracy one is tearing, and the alternative inaccuracy is running the machine at slightly the wrong rate. And I decided, the tearing is more inaccurate than running the machine at slightly wrong rate. I don't know, it was a qualitative decision. It wouldn't necessarily stand up in court, but there it is. So, yes, latency, the current emulation frontier. If you've been on any sort of emulation development board or forum recently, you will learn that everybody is, I'm going to say, suddenly obsessed with latency. I don't think that possibly misportrays what's happened here, which is that a very long time ago, we realized we could do cycle-accurate emulations of almost anything. I mean, you've got cycle-accurate spectrum emulators from the 90s. This is, we're 20, 25 years into this. 25 is an exaggeration, but still. So, what can we improve next? And people have said, why don't we try to improve latencies so that it's easier to play our games and not miss all the jumps? So, yes, and with my advantageous development position of having a 30 hertz display, I can really spot when an extra frame or two is delay is there within the pipeline, and therefore I've become a convert to this obsession with latency. But I will accept that, most people, a lot of people don't care. Like, everything was fine before we got obsessed with latency, but here we are. So, in my emulator, the machine itself, whatever it may be, that is always being updated somewhere between 600 to 1,000 beats a second. That is to reduce the input sawtooth. So, the 600 to 1,000, that depends on which version of the emulator you're using, in the sense that I currently officially support both a Cocoa build and an SDL build, and the bindings to Cocoa, i.e. macOS, or SDL, sit completely outside of the main emulation loop. The bindings themselves decide at what rate they're going to tick the machine, because the interface is, hey machine, run for X nanoseconds. So yeah, the discrepancy there is just, it's based on which version you're using. It's not based on what your computer can run. It probably should be. This is a point of potential future improvement. So that reduces input latency, because if you have a more traditional game-like emulator loop, which in the the knee-jerk basic version goes something like, wait for vsync, here is vsync, so check all the inputs and update the state with my emulator. Great. Draw another, run for another frame, get the frame at the end, post it to the video card for display at the next vsync and block, which buys you like an average of, I mean, it's half a frame's latency, I guess. Average, is it? No, I guess it's 1.5 if I'm going to grab input at the start. But the point is, the input that is actually applied to the machine is already historical by the time it's applied. That's unavoidable. And the size of the window that you permit in between each sampling of the input is therefore a sawtooth wave on the input. I feel like I'm over-laboring this point. And the higher the resolution at which you check the input, the lower the average latency will be. There you go. That's a very simple way of getting to that point. The emulator aims to have a target audio packet size of only 256 or 512 samples, which is, compared to the way these things often run, that is a very small amount. So that is an attempt to minimize output. But important disclaimer, I haven't been able to achieve that very well in SDL, and the Qt port, which is almost ready, and I will maybe drop in again on later, the Qt port also seems to force a minimum of 2,048 samples, and even then the documentation isn't explicit on whether that's the size of the ring buffer or the size of individual packets, so it may be even worse than that. It's the amount I'm allowed to put into the ring buffer the very second that the audio pointer skips into the other side of the ring buffer. So audio latency, that's great. I've got a target number, and sometimes I hit it. Life is nice. There's the attempt to pull sync into phase, which I mentioned at the end of the previous slide. There is a potential advancement on this. It is being pushed around by, oh my gosh, I'm the worst human being, by the guy that runs the Blurbusters forum, whom I respect a lot, but apparently do not currently remember the name of. So here's the point. Thinking about it this way. The machine is ticking at, let's just stick with 1,000 beats per second to keep the discussion simple. And you know that the host machine's vertical sync is occurring at the same time as the emulated machines. So that means that when you run a tick that appears to be halfway through the frame in terms of the emulated machine, then that should also be about halfway through the frame on the host machine. Great, so we're kind of racing the raster here, but here's the clever bit. If you have only a single buffered OpenGL view, or other frameworks are also available, then often when you ask to switch the buffer, it will switch instantly. That's why you see tearing in a lot of games where you've disabled vsync. So, technically, if you know how far you are down the frame, and if you can change what's about to be drawn at any time, then you can fully race the raster. So now you're no longer talking about frames worth of latency, you're talking about lines worth of latency. And there are sample apps out there that demonstrate this. I think there's also a test implementation of MAME and of UAE, i.e. the big boy emulators, that prove that this is not just a theoretical win, it's a potentially huge win. Like, it knocks out so much of the difference between the way that we run emulators now and the way that classic machine actually drives the raster in real time, albeit that there's still sometimes some buffering in the monitor or in the operating system, so it's not exactly as good, but it's a huge win, and I am almost there, but I'm not quite there yet because I do not have an effective way to test this in a continuing fashion, which means that I, who am now aware of my own development habits, I'm sure that if I were to flip that switch, then it would work fine on the day I flipped it, and maybe for a few months afterwards, and then it would break, and then I wouldn't realize, and then I would be walking around going, oh, look at me, I'm racing the raster, and I'm not, I'm just lying to everybody. Well, I'm mistaken, it's not malicious, but so when I can think of a way to force myself to test that routinely, I will bother implementing that. At the minute, that is most easy to do on Mac OS because, as per the final bullet point, some of the other platforms that I'm bought into, in fact, both of them, because at the minute it's still only Mac OS, SDL, and 95% there on Qt. Those are both cross-platform APIs, and they tend to offer a relatively reductive set of features. Specifically, they tend to offer only the common pattern whereby, as a piece of software, you can say, this is my next frame, and I want you to display it when vsync occurs, and I want you to block until then. And that is the only mechanism by which you have any insight into when vertical sync is occurring, which is, it's difficult in terms of racing the raster. As you can see, I've been, for the purposes of Qt, which appears to be even worse for latency than SDL, because I think they have an extra frame buffer in there, because of course they're compositing a bunch of controls and things, and fair enough, it's not meant to be an API for gaming. They've done a great job at what they intended to do, and maybe I shouldn't be using it for the wrong purpose. But yes, so what I have currently been working on is keeping a full record of how long different steps of the drawing infrastructure seem to take. It's a simple thing, it's just a mean and the standard deviation. And then using that, I can predict how long a frame draw seems to take on this architecture. And I'm also monitoring how precise the delay timers are, how much jitter there is in those. And based on all of that, I can attempt to push my frame draws to the very last moment that I can, carry them out without missing the next frame. And that is the only way I've found to, I guess, match myself to vsync while not spinning and occupying 100% of the CPU. Everybody was, again, that would make the thing basically unusable on modern hardware. Your battery would go in a second, your fans would rev up. You would say, who is this idiot? Why can't he write software? To attempt to deal with that, yes, to try to capture the current output at the last possible second for presentation. Life is a lot easier on Mac OS. You can just register for, let's just call it the vsync interrupt. It's not obviously that simple nowadays, but you get a signal on its own, dedicated, high precision thread, which tells you vsync just began, it should last this long, the next frame should take this long, and by the way, the frame rate is all of these other corollaries of that. That's a completely independent signal, and you can just do whatever you want with presenting graphics separately from that. especially on macOS, the timers are really high precision. You want them to be like nanosecond precision. It is absurd. I can see why they try to sell this thing so much to media types. They put a lot of work into that. Good for them. I wish they wouldn't charge so much for it. But yes, good guys, probably, for all I know. When you have the macOS way of doing things, it is a lot easier to race to Raster than it has been with the cross-platform APIs. I will say that the immediate future for clock, thanks to Apple and the WWDC, is likely to be that I will finish off this Q port, hopefully. The keyboard has proven to be the blocker. I really don't like the way the Qt does the keyboard, but I will muddle through and somehow make it work. It's basically finished, but for that. Finish that, then I've got to follow through on having an optional metal alternative to OpenGL on the back end, which I'm sure is going to be a pain because I don't currently know any metal, although I do understand what I think I know about GPUs in Mac world. And of course, now they'll be very similar to the ones we've had on mobile for a long time. So hopefully all those lessons learned will apply. Then I will have a version for macOS that doesn't become broken as soon as the, I don't know what we're going to call them, the Archimedes. That's probably, yeah, throw out the MacBook name, bring in Archimedes. As soon as those come out, at the minute, I will lose the ability to build for new silicon, Apple Silicon. Oh, imagine that with capital letters, not a proper noun. I will lose that because they are not planning, as far as I can tell, to continue to offer OpenGL at all on the new systems. They deprecated it a couple of years ago. We all had warning. I am half ready for this. It used to be that every machine could produce its one-dimensional video output stream in any format it liked, as long as it also gave you the GLSL to decode that to any of composites, S-video, or RGB, as per whatever the system actually supports. When Apple deprecated OpenGL, I, of course, had to do away with the idea that every machine can use its own pixel format and supply its own GLSL, so at least that's all regularized now, and there's just one spot where I have to provide alternative metal implementation. That is way off topic. After that, I hope to finally look at doing a Win32 port, because I would have just done one new toolkit, one new graphics backend, so I figure another new toolkit and another new graphics backend will hopefully be looking a lot easier by then. If not, I guess I could just reuse OpenGL on Windows, but I know that's not ideal. Moving on. So, things I'm going to do next in terms of machines. This is actually the final slide. There is some time for, I'm not in charge of time. If there is time, then I can demo the emulator a bit. I know that being macOS exclusive means, well, not macOS exclusive anymore, but originally and for a long time macOS exclusive, and subsequently until very soon without a UI on other platforms, means a lot of people want to have used it. So yeah, can demo that. But otherwise, these are the Acorn machines I was thinking of implementing into my emulator in the near future after I finish doing all of those other things I was talking about, possibly. Or maybe I'll change the order again, I don't know. This is why it's a hobby project, because it's things that are fun. The priority is anything that sounds like fun. But I would love to add the Atom. It's a multi-machine emulator, so part of the, let's pretend this is strategy and call it the strategy, is looking at what machines you can implement that will give you a bunch of tools that will propel you to be able to do a bunch of other machines, because as well as optimizing for fun, another thing to optimize for is number of pieces of software that you can run, which possibly is why sometimes I don't quite finish off on the cycle accuracy thing, because it is arguably more time efficient to implement another machine. I don't know. It's very ad hoc set of decision making. Anyway, the Atom will get me a 6847. I've also never used an Atom in real life. It would be the first machine I implement where I actually had to worry about display snow, so that would be fun. And it has a popular SID add-on, so hopefully I could get the SID working without having to try to do a Commodore 64 and embarrassing myself too much in the process. Side note on that, recently added the 68,000. Actually, I did most of that last year because I was on gardening leave. Non-compete agreements are enforceable here. Oh, I live in America, by the way. This is New York. Everything's 30 degrees. It's going to be sunny for longer than it is there. Don't be surprised. And after the 68,000, I implemented Macintosh, and those were the first two times that I thought, wow, this is possibly I've bitten off more than I can chew here. But I got through them, so more valuable learning experience there. The emulator as a whole has been fantastic for having things to say at interviews. That's why I would recommend anybody write an emulator if they're like me and prone to interviewing often. Gosh, that is a very flattering way of describing my career path. I'm on LinkedIn. Check it out if you care. You probably don't. The BBC Micro. Great. So, as I said, I've implemented the Amstrad CPC. I'm going to assume I did say that at some point. So I have a 6845 working, and it works mostly, but clearly something is still not quite right. It is implemented, half cycle by half cycle. Every one of those, it just does compare this register to this register. If so, set or disable this piece of state. So, it should be. I don't know why it isn't quite perfect. There are various CPC demos that do not quite run correctly, so something is wrong. And speaking selfishly, apologies, if I were to implement the BBC Micro, I feel like I would find out that a bunch of things on the BBC also didn't work, but thanks to you fantastic people, I would be able to say, tried running this one of Sarah's demos or whatever, didn't work, wonder what I might have done wrong. And probably somebody would just be like, oh, it's this, you idiot. You're such an idiot. I can't believe you did that. And then that would help me. That would help the emulator, that would help the Amstrad CPC. Actually, surprisingly, it seemed to be nearly the only current updated, maintained open source Amstrad CPC emulator. So I get a lot of feedback about that one. Otherwise, as to the BBC, things I already have implemented, which is why it is not necessarily out of reach. Obviously, the 6502, the 6845, I've got a 6850 because it's one in the Atari ST. The SN76485, of course, is in in the master system. What else have I got? 6522s, plenty, which seem to be. I mean, I've run timing tests on those quite a lot, and they're used in a number of very diverse ways by the machines I support. Believe it or not, the Macintosh actually uses, the original Macintosh up to at least the Plus, and I think onwards, actually uses the shift register and the 6522 with an external clock, which famously has a terrible race condition. It's basically never used. That's why the Commodores do a software polling loop for reading their disk drives rather than a hardware loop, and it's why their disk drives take like 5 minutes to load a game. You might as well just load it from tape. The Macintosh uses it and gets away with it. And it does that because it is only ever transferring a byte or two at a time. It's never transferring big chunks of data, and it has a pretty strict retry mechanism. Specifically, it's interfacing with its serial keyboard via that shift register, and the keyboard is running the clock. But point being, lots of machines, lots of uses in 6522s. I would hope that mine are reasonably thorough. They've really been. I have not enjoyed implementing the 6522. Let's just say that. The documentation tends to be very circular anyway. Other good things about implementing the BBC Micro would be that I could finally play Repton with big graphics. I could play Chucky Egg with more colors. It would all be a big win. But on the flip side, it's another one of those platforms where there are already a bunch of fantastic emulators. So exactly who am I helping there other than myself? If I'm only helping myself, then I can't necessarily justify that action. So also, the ARM would be great because this is a potentially interesting direction point. All three of my current processes are implemented internally as microcode. So for, 6502 is obviously the simplest one. 6502, there is a common piece of microcode that fetches a byte from the program counter and increments it, and then another byte from the program counter, because the 6502 always fetches an argument byte, whether or not the instruction is going to need one. And then, based on the instruction that was fetched, it looks up a table of other micro instructions, and then it just plows through those. And some of them are zero costed, and some of them are bus accesses, which cost 1 cycle. And it just has a program counter into a system microcode, and that is how my modern implementation of 6502 can run for any number of cycles, pause at any point, and will always make the appropriate bus accesses at the appropriate time. So what that amounts to is there is a big lookup table of microcode by instruction, so like a 256 entry thing. The other processes work similarly, but it gets a bit more convoluted. Obviously, the Z80 has multiple tables of these things because of the way that they extended the instruction set from the 808 there. And they tend to have a bit more nuance to them. On the 6502, it's just like each one is a single entry within the num. So it's a 1 byte entry, which is nice and cache efficient. But on the Z80, possibly I wasn't as careful as I should be. Each one is an action plus a source and a destination. And the instructions tend to be, small things like copy this to this or add this to this and set the flags appropriately. And the 68,000 is where things really get epically convoluted, because the standard instruction size on a 68,000 is 16 bits, not 8, so that's a bigger table. And the instructions tend to do more. It's very CISC-y, it's like peak CISC, except it's not, because of course there's the, say, the 6804 is obviously more peak CISC than the 68,000, but that line is peak CISC. And the cache is only so big. So there's like 2 levels of indirection in there, and it is built at runtime by a disassembler. So I don't actually have to understand how the tables are formulated, which is nice, because I can understand, having written it, and I am very verbose with comments, so thankfully I can still understand how all these tables are built, but maintaining them, I wouldn't like to have to. If I were doing it like a lot of other emulators do as a pre-processing step, and then I wanted manually to edit the output, I think I would get very lost very quickly. So the ARM is very appealing, not just because all Macintoshes are about to be based on it, or the modern version of it with a whole status register of its own and everything. I believe that that would be an instance of a processor that you could implement successfully using pure programmatic opcode decoding at runtime, no tables, which would be a breath of fresh air. That would be fantastic. So the first generation of Archimedes, also because, well, look at my face. The Archimedes were clearly the computers that were in schools when I was, secondary schools anyway, when I was a child. So I have a very strong emotional attachment to them. And also, no, I don't really want to get into, so I've had personally difficulty getting any other Archimedes emulator to run that well on macOS. That might be because I'm an idiot. If you have written one and you're watching this, I'm not saying anything about your work. I am just telling you that I am an idiot. Good. Moving on. Yeah, so the emulator still doesn't have saved states or any sort of debugger. I think it may be the only emulator in the world to have lived 5 years and not gained a debugger or saved states. And the issue there is that the processors are written so that they are bus accurate. That's what I prefer to this nebulous concept of cycle accurate, where, I mean, if you pull it apart, the phrase cycle accurate kind of means here is a discrete clock, and within each of the windows dictated by that clock, I have seen what should occur, and I just pin them to the start or the end of the window. I guess that's kind of arbitrary. So it's just a measure of timing precision, and it is not always a useful one. BBC Micro being a fantastic example, if your 6522 were only cycle accurate, then it would trigger interrupts at the wrong time, because it is on the 1 megahertz bus, which means that the fact that it raises the interrupt signal halfway through one of its cycles, the 6522 cycles, means that it would be, if you put that at the end of the cycle accurate 6522's run, it would be half a cycle too late, which is 1 cycle for the 6502, which is a measurable amount by software. I'm pretty sure that is all true. I'm sure I will learn shortly if some of that is not true. So yes, bus accurate means that I have implemented my processors so that the only thing they have to get right is to announce their single atomic bus steps, which on a 6502 are always 1 cycle long. On a Z80 tend to be like 1.5 or 0.5 cycles long. Those are like the modal numbers. That's not guaranteed. On a 68,000, they tend to be 2 cycles long, but they can be longer. They only have to, my processor emulations only have to announce the correct things every time on the bus. What they are doing internally and how accurate that is to real processors is their own business. And because it is their own business, I am worried about tying myself down to a particular internal scheduling, which makes capturing state in a rigorous fashion that is safe between versions of the emulator. More troublesome than it would be if the emulator were knowingly less accurate. But I have simply bitten the bullet on that. So I've started, it will take a while to permeate through the entire emulator, but I've invented my own version of sort of introspection in C++. You know, that's always a bit, there's always some extra effort required because the language is not natively supported. Oh, how I pine for that one feature of Objective-C. So my aim is that, you know, these save states will just look like whatever, structs, but they will be fully introspective. So bang save state is also debugging because any state can be fully inspected and altered and reinstalled and run. So I'm kind of doing those two things together, and I was doing them perfectly happy until I was blown asunder with this whole Qt endeavor. That's Qt, by the way. If people have read about the framework Qt and haven't realized that people use it like to pronounce it Qt, that's the Qt I've been referring to all this time. You know, it used to be owned by Nokia, isn't anymore. Lucky them. So yes, something else I tend to do is when people ask me for things, I feel like I should do them. So I'm very easily distracted. Somebody asked for a Qt port. I've been working on a Qt port. I got some press a week and a half ago, not some press. I was listed on, somebody found the composite encoding and decoding feature of my emulator interesting, posted me on Y Combinator News, and I got a bunch of people asking for a Windows port. That's why that's suddenly been bumped up the roster. That's actually the end of my slides, so I'll do a few more words on how the composite encoding and decoding works, because again, apparently that's interesting. And then I guess I will show a demo, but it's not that interesting. I mean, it's just an emulator running some software, nevertheless. So if you use the emulator and you ask it to, and that's a big if, by the way, yes, and if you ask it to use a composite display, then what it will do is it will do an actual composite encoding and decoding of your video data in an attempt accurately to portray what composite video looks like. Now, it doesn't necessarily do a good job, but that is what it is seeking to do. So in an earlier implementation, and this will soon be future implementation because it was a better idea and I will be bringing it back, that's achieved in the following manner. So what the emulated computer has supplied to you, you being the screen in this case, is, you know, after it has been turned into scans and it's come out the other end and you want to plot it to the screen, it's like a bunch of runs that say, I started at XY here and I ran down to XY here, because of course scans are diagonal on TV screens. And this is the pixel data that was emitted during that time. It is however many samples it is, and here it is. So then that is just stretched and filled into a, you know, quad that size on screen. In my emulator, every raster scan is drawn individually. There is no, you know, output a whole frame thing. Anyway, so some machines produce composite video natively, or close enough. Say the Apple II. You actually have to, you know, put in the ones and zeros that produce the correct colors in composite terms yourself. Most don't. Most, such as the Electron, have an internal sense of RGB, and then they just encode that as composite for display. And what my emulator was doing was picking the least integer multiple of that clock rate is at least 4 times as large as the color clock. And there was scaling up to that, doing a discrete composite encoding at that resolution, running a low-pass filter over that to separate luminance and chrominance, doing some more filtering on that to remove noise, because, well, in the color signal, that is. The color signal, when you've extracted it, still looks like an amplitude, quadrature amplitude modulated thing. Well, I guess 2 amplitude modulated things. So you still have to filter a bit more even after you've separated it. Anyway, then all that ends up on the display. Nowadays, I'm doing something else, which is an attempt at a cone filter, which unfortunately has some aliasing problems, which I don't really like. It was an attempt to improve performance, whatever. It is nevertheless a genuine attempt to decode composite video, which just isn't as good as the other one used to be. It does it in less time, but I'm thinking, you know, be on the right side of history of this, let it be a bit slow on my computer. Here I am I like very small computers, and I like to keep them for a long time. So I am nowhere near representative of the modern state of processing hardware. Tripping over myself there, I'm not representative of it because I'm a human being. My computer isn't representative of it either. So yes, then it has a full composite signal decodes it displays on the screen. In principle, that should mean that you get things like dot crawl and you know, other color fighting and false color rainbows and such like. So they just appear naturally. But yeah, more work to do, hopefully. I mean, it already works pretty well, to be honest, but everything could be better. So at the minute, it's a bit chunky. It's a bit, you know, aliasy. Also, I think I might have a race condition in the way that I manage the OpenGL threading, because when the emulator gets really slow, sometimes the graphics jump about, but I really need to look into that. I'm hoping it's not a false assumption about memory sequencing or about cache coherent guarantees, because again, Apple are about to switch to ARM processors, which have different guarantees on that sort of stuff. So if I'm accidentally relying on, you know, specific x86 behavior and getting away with something, then that's not sustainable.
Just going to say very quickly, absolutely fascinating. I've just posted onto the comments actually the Doomsday 86 project that Simon did a talk about 10 o'clock this morning our time. Has had to implement PAL and NTSC comb filters that are well, the PAL one is so good that we know that some people at the BBC are comparing it against their R&D one.
Okay. I mean,
and we have had input from the BBC on what to fix, etc. I'm not involved in the code on that, but I just thought I'd mention it because it's open source GPL, and I've just dropped a link.
oh, cool. I'm sure that does a better job than I can.
Yeah, there's also NTSC, and you do get dot call out of it because it hasn't got a 3D comb filter yet for NTSC. But
oh no, so I've specifically decided not to do a 3D comb or anything modern that looks too good. I'm trying to make it look like you're using a 1980s computer with the sort of 1980s screens that people had. So in my case, it would have been something that cost about 80 quid secondhand from radio rentals when they, you know, when the world stopped renting. So in some regards, I spend a lot of time trying to make the composite video look better because then I'm doing a better job of my objective of doing it for real. But you know, there is a ceiling to that.
Yeah, well, as Simon brought up earlier, we did a PAL decode, and then the HackRF guys decided to pick it up to do a PAL encode so that they can stream out composite video real time from HackRF. So there's a PAL encode as well there.
Again, probably more rigorous than mine. Again, this was... So I obviously stepped away from emulation for more than a decade. I stepped back because I was starting at Google. I didn't know C++, and I wanted something that was, you know, very C++y to learn from. And I'd done the earlier clock signal, which was emulating the ZX80, which has some aspect of trying to emulate a screen, but I'd done a very poor job. So a lot of it was just to have fun learning these things. That's when I started picking up the textbooks. And therefore, my knowledge of exactly how to decode a composite signal PAL or NTSC in a rigorous fashion is likely to be a lot lower than anybody who has ever discussed it with another living human being.
Yeah, well, it's we started off a similar situation, but got sent a lot of documentation.
Cool.
So, my 3-year-old on the sofa.
On that, yes.
Cheers, anyway. Great talk.
No, thank you.
I don't think we really are going to, unfortunately, have any time for any further questions right now. Sadly, we're going to have to draw a line under this topic. Thank you very much indeed for that really very interesting talk and a very impressive piece of software. I certainly in the background had downloaded the release from your GitHub and was playing around with it. It's very impressive indeed.
Oh, cool. And if you want to try the Qt port, it is on GitHub in the Qt project branch, and it mostly works. The problem is just they do a weird thing with modifiers and keys, so it may not always read keys correctly if you're also holding a modifier.
Hi again everyone, welcome to a re-recording of the clock signal emulator demo, no longer a live demo I guess. Here I am loading Racing the Beam, one of ZeroXCode's demos, in composite television mode. There it is, down there. I will warn you that this computer skips frames a little bit when I'm also recording video, but here it is. And of course RGB mode is an option, just as it was on a real machine, and the window is freely resizable because again it is attempting to emulate a real CRT scheme and just make snapshots of that for you. It is not doing any sort of one-to-one pixel copying or any sort of calculation like that. Let's load something else. In fact, let's load two other things. Why not? It's that sort of emulator. Loading things is not the only way to get into an Electron, of course. You can just start a new machine at your leisure. Here is a ZX80, a noticeably worse machine than the Electron, but that is evidence perhaps of the way that the emulator handles sync discrepancies. I also mentioned in the speech that a Qt version would shortly be forthcoming, so here it is in Ubuntu. There's the interesting machine. Those other ones, yeah, they're okay I guess. Let's start it up. Here's the Electron for you. I can think of nothing particularly interesting that I know how to write quickly in BASIC, so let's draw a diagonal line being over 2000% more interesting than a horizontal line. There you go. There is the emulator in Qt running natively on Ubuntu. I will leave it there. Thanks for watching.